Hello everyone, we're going to be going over section 9.4, which is going to be on vectors. So we have 7 objectives in this section. First, we want to graph vectors. 2, find a position vector. 3, add and subtract vectors algebraically. 4, find a scalar multiple and a magnitude of a vector. 5, find a unit vector. 6, find a vector from its direction and magnitude. And 7, model with vectors. So quite a few items in total with vectors here, so let's get started with some introduction before objective 1. So a vector is a quantity that has both a magnitude and a direction. Usually you represent vectors, by using arrows where the magnitude is represented by the length of an arrow. With geometry in vectors, P and Q are distinct points in the xy plane, and there's exactly one line containing both P and Q. We call all the points on the line between P and Q, including P and Q, a line segment PQ. And that line segment, we include a bar that goes over PQ to indicate that this is a line segment with points P and Q. Ordering the points so that they proceed from P to Q is called a direct line segment from P to Q, or a geometric vector denoted by PQ now with an arrow instead of just a line. In a directed line segment PQ, arrow, P is called the initial point and Q is called the terminal point. So we look at our images here for part A, we have a line containing points P and Q. For B, we have our line segment P and Q, so our line ends at point P and Q. And then for part C, we have our directed line segment P to Q. So we have an initial point P, and we're showing that this arrow, this line, is now going to Q. And we signify this with an arrow instead of a solid line segment, where you start at P, so that's your initial point, and you go until Q, which is then your terminal point. The magnitude of the directed line segment PQ is the distance from P to Q. So magnitude is just going to be distance, or the length of the line segment. If a vector V has the same magnitude and direction as the directed line segment PQ, then our vector V is equal to the line segment, the directed line segment PQ. So whenever we refer to a vector V, we're going to draw it as V. Typically, you can see V with an arrow above it as well. So you see V with an arrow. The way that I do it, because it is much faster, it kind of looks like an arrow that's missing half of its pointy side. So kind of just a line and back a little bit. That's how we indicate a vector. If you look into your book, the vectors are just indicated by the bolded letters V and W, or any other vectors that you indicate. So there's definitely different ways to indicate that something is a vector, but typically the most common we see is that there is an arrow, or this little half arrow above it as well. And in your book, it's going to be bolded. So then the vector V, whose magnitude is 0, is called the zero vector, or just 0. The 0 vector has no direction in that case. So two vectors, V and W, are equal, written as vector V is equal to vector W if they have the same direction and magnitude. So if we look at our image, we see P to Q, R to S, and T to U. All of these line segments are all equal because they have the same direction and they have the same exact magnitude. So if we want to think about adding vectors geometrically, the sum, vector V plus vector W, of two vectors is defined as a positioning of vectors V and W so that the terminal point of V coincides with the initial point of W. So if you start from your initial point V and you go to W, and then you add from the initial point of W to the terminal point of W, and then you go ahead and you connect those lines to create your one solid line of V plus W. So then here are some properties of vector addition. We see vector addition is going to be commutative, so that V plus W is equal to W plus V. Vector addition is associative. So if you have something like u plus the sum of v plus w, that's equal to the sum of u plus v and w. Then the zero vector 0 has the property that v plus 0 is equal to 0 plus v, which is just equal to v for any vector v. Then we also have that v plus negative v is going to be equal to 0. So typically your identity property is what that's known as. If v and w are two vectors, then the difference v minus w is defined as v minus w is equal to v plus negative w. So essentially, subtraction is just going to be rewritten as addition with opposites instead of actually written as subtraction. Then multiplying vectors by numbers geometrically. When using vectors, real numbers are referred to as scalars. So instead of calling them real numbers, we now know them as scalars, or quantities that have only magnitude, so no direction. We can now multiply scalars and vectors. So the definition of a scalar multiple is that if alpha is a scalar and v is a vector, the scalar multiple of alpha times v is defined as follows. If alpha is greater than 0, alpha times v is the vector whose magnitude is alpha times the magnitude of v and whose direction is the same as that of v. If alpha is then less than 0, alpha times v is the vector whose magnitude is the absolute value of alpha times the magnitude of v and whose direction is opposite of that v. Then if alpha is equal to 0 or if v is equal to 0, then alpha times v is then equal to 0 as well. Scalar multiples then also have the following properties. They have that 0 times v is equal to 0, 1 times v is equal to v, negative 1 times v is negative v. Alpha plus beta times v would be alpha times v plus beta times v. Alpha times v plus w is equal to alpha times v plus alpha times w. Then lastly, alpha times beta times v is equal to alpha times beta times v. So those are our properties of our scalars. All right, so done with the introduction, now we're on to objective 1. We want to graph these vectors. So our first example, we want to use the vectors in this figure to graph the vector 2 times v minus w plus u. So we have each one of our different vectors here. Wrong color. There we go. We have each one of our different vectors here. Now, it's important to know how long, what direction that each one of these vectors is going to be in. So let's begin by writing these out. We see our vector v is going to go up 2 and 3 to the right. So we know that this is our direction of v. Then w is going down 2 and also to the right 2. This means that if we take negative w, this would then be flipped. So it would now be up 2 and to the left 2. Then we have u. It's going to be up 3 and right 1. If we have 2 times v, this would end up being up 4 and to the right 6. So we just multiply those values by 2. So here we have it. Here we have the direction and magnitude of each one of our different vectors, and we just want to plot them in our box here. So if we go ahead, let's start about right here. This is going to be the initial point of 2v. So remember, we're going to go up 4 and to the right 6. So we're going to go 1, 2, 3, 4, 1, 2, 3, 4, 5, and 6. So we've gone up 4 and we've gone right 6. So now we're going to draw our arrow to this point. And it was close enough. So this point here is 2v. Now we want to connect this point so that it is connecting with negative w. So this needs to be the initial point of negative w. We know the negative w is going to go up 2 and to the left 2. So this value here is going to be negative w. Then lastly, we want to add u, and u is up 3 and to the right 1. So we're going to go 1, 2, 3, and then 1 to the right. And we draw our arrow that way, and we know that this is also the vector of u. So now what happens is that we want to connect the first point and the last point. So we're going to be connecting the initial point of 2v and the terminal point of u. So we're going to grab and connect. So now this line here, which I think I'm actually going to change to be a better color, so it is more obvious to see. This value would be our vector 2v minus w plus u. So when doing problems like these, you want to make sure that you make all the correct alterations first, kind of go through what your magnitude and direction will be for each individual vector, and then when you graph it, go ahead and just make sure that each one of those is going to be correct and make sure that you are connecting your direct line segments. All right, so now we have the magnitude of vectors. The symbol v with double bars on each side represents the magnitude of a vector v. Since the magnitude of v equals the length of a directed line segment, then it has the following properties. So the properties of the magnitude v of vector v is that if v is a vector and if alpha is a scalar, then we have that the magnitude of v is greater than or equal to 0. The magnitude of v is equal to 0 if and only if v is equal to 0. C, the magnitude of negative v is equal to the magnitude of positive v. And then we have that alpha times v, or the magnitude of alpha times v, is equal to the absolute value of alpha times the magnitude of v. So these are going to be our basic properties of magnitude. Then we have the definition of a unit vector. A vector u for which that the magnitude of u is equal to 1 is going to be called the unit vector. So we're going to need that very shortly here. Objective 2, we want to find a position vector. To find the magnitude and direction of a vector, an algebraic way of representing vectors is going to be needed. So an algebraic vector, v, is then going to be represented as v is equal to the ordered pair a, b, but now we see our parentheses, which aren't really parentheses, are now essentially going to be these kind of angled arrows. So they're not quite parentheses. When written out, we'll normally write them as a, something like that. We see that a and b are going to be real numbers or scalars called the components of the vector v. So whenever we say components, these are the values that we're talking about. If the vector v is equal to the components a and b is an algebraic vector whose initial point is at the origin, then v is called a position vector. So that's only if its initial point is at the origin, so 0, 0. Any vector whose initial point is not at the origin is equal to a unique position vector. So which leads us to our theorem here. So suppose that v is a vector with the initial point p sub 1, which is equal to x sub 1 and y sub 1, not necessarily the origin, and a terminal point p2, which is equal to x2 and y2. If v is equal to the direct line segment p sub 1 times p sub 2, Then v is equal to the position vector. V is equal to, and then we have our components, x sub 2 minus x sub 1, and y sub 2 minus y sub 1. And we can say that two vectors v and w are equal if and only if the terminal point of v is the same as the terminal point of w. So we have equality of vectors. Two vectors v and w are equal if and only if their corresponding components are equal. That is, that if v is equal to the components a sub 1, b sub 1, and w is equal to the components a sub 2 and b sub 2, then v is equal to w if and only if a sub 1 is equal to a sub 2 and b sub 1 is equal to b sub 2. So those are the only cases in which our vectors v and w would end up being the same. They would need the exact same components. Now, we're going to let I denote the unit vector whose direction is along the positive x-axis, such that I is equal to the components 1, 0. Then we let j denote the unit vector whose direction is along the positive y-axis, such that j is equal to the components 0, 1. Any vector v is equal to the components a and b and can be written using the unit vectors I and j as the vector v is equal to the components a and b, which is then equal to a times the components 1 and 0, plus b times the components of 0 and 1, which then simplify down to be a times I plus b times j. The quantities a and b are called the horizontal and vertical components of the vector v, respectively. So a is your horizontal component, b is your vertical component. This also, if you could guess already, corresponds to your x and y axis. So a is going to be on your x-axis or your horizontal axis, and b will be on your y-axis or your vertical axis.